Okay, what I had already been covering and what I derived, I believe, was the exponential Fourier series. Here it was. Here's the Fourier series. Given that it's the original functions defined on this symmetric interval minus p to p. And here were the Fourier coefficients. I already did that. Using Euler's formula, you can express this e to the I stuff in terms of cosines and sines. I can convert e to the I stuff to cosines and sines, then do some algebra to it. And from the exponential Fourier series, come up with this other Fourier series, which is really the same Fourier series, but with different terms, cosines and sines. And I would have the formulas for these little a's and b's. Here are those formulas. So this is the trigonometric Fourier series, which is really the same thing, but expressed differently. And this might be what you've already seen. You hadn't seen the exponential Fourier series. I could have derived this directly. Remember, we derived this using an orthogonal set. And the orthogonal functions were these guys, e to the I guys. Well, it turns out that the set of cosine n pi over p, sine of n pi over p, pi x over p, and 1, an infinite set of functions, is also an orthogonal set. And I could have derived this directly from that orthogonal set, kind of the way I did the exponential Fourier. Some intuitive concepts for these things. Let's say here's the original function. Find on a symmetric interval, -1 to 1, 0 on the negative side, and 1 on the positive side. So that's all the original function is, right there, from -1 to 1. But its Fourier series will converge to this thing graphed here. Remember, I can graph it without doing any calculations. The original function, and then repeated every 2 periods. Here, the total period is 2, -1 to 1, or 2p. P is 1 here. So I just get a bunch of clones of the original thing, repeated every 2 units of x. At these points of discontinuity, it converges to the left and right limits. Here's what's interesting that you could do more with the trig function than with the exponential one. I could take a partial sum. It's kind of hard to do an infinite sum. But I could, with a computer or something, I could take a sum up to some finite n. And say I did for some finite n, and use the computer or something, its graph might look like this squiggly line. And the bigger the n is, the closer that will look to what it will ultimately converge to. Do an example. I don't want to get too bogged down in the calculus of this. Let's say here's our function. It's only defined from -pi to pi. In this case, p equals pi. Period would be 2 pi. Let's see. I have 3 different things to compute, right? I have a0, a sub n, and b sub n. Plug them into the formulas. F of x here equals, I have to break it up because it changes signs. But go through that simple calculus, you get a 0 for the a's of zeros. What about the a n's? Plug it into the formula. I have to break up the integral into 2 pieces. Do that fairly easy calculus. I get a 0 again. What we just learned about odd and even functions, well, I guess we'll get into that in the next charters. For the b sub n's, plug it into the formula. Got to break up the integral again. Fairly simple integrals. And here would be an answer. But from before, you should know that the cosine of an integer number of pi is -1 to the n. So I can replace this cosine of minus n pi with -1 to the n. Replace this guy with -1 to the n. Now we get two guys are the same. I can put them in one. So here's my B sub n's, my Fourier coefficients. You could look at it like this. It's going to be 0 for even n's. Anyway, when I put it back into the formula, the only thing left is b's, the formula. Here's the formula, actually way back here. Here's the formula. But if all the a's are 0, all I'm left with is the sum of these ones with the b coefficients. That's what it is, and that's what it looks like. I wrote it out. Maybe I'll talk about it right now. You should have been able to recognize this is an odd function. So let me I'll cover it later. Let's talk about the cosine and sine series now. Because look, what if your function is even or if your function is odd? Here is the Fourier trigonometric Fourier series. Here's the coefficients. Cosine is an even function. You know, we're worried, is it with respect to x here? The variable is x. The cosine of something is an even function. The sine of something is an odd function. So now let's look if the function itself, the f of x, is even or odd. If it's even, look at the b's. I'll have an even times an odd, which means the integrand becomes odd over a symmetric interval, so all the b's go to 0. And for the a's, I'll have, that's an even function, so I only need to integrate from 0 on up, as long as I multiply by 2. Here I have an even times an even, same thing. So my a sub zeros, my a's are just multiplied by 2, and I only need to integrate from 0 on up. It's odd. If the f of x is odd, here I get an odd times an odd, so that's even. So I can multiply by 2 and only have to integrate from 0 on up. But all the a's, I'm integrating an odd function over a symmetric interval. All the a's are 0. And that's what happened in the case we just did. We could have known right off. We didn't have to compute the a's. You put it all together. If you know you have an even function, it simplifies. Use this middle column. If you know you have an odd function, use this right column. If you're stuck with finding the Fourier series of a function that's neither even nor odd, you're stuck with this left column. That's the general formula for a trigonometric Fourier series. So like I just said, the example we just did, now we recognize it as odd. So we just use the sine series. We do the same bit of, almost the same bit of calculus, but now we only have to integrate one section from 0 to pi, multiplied by 2. Didn't have to explicitly break it up into 2 chunks. So it's easier if you know going into it if your functions are odd. Here's a function of another odd one, either plus pi or minus pi. Looks like that. I'm not going to go through this calculus, but we know we only need to compute the b's. I'm going to go through this. This should be calculus you should be able to do. One last example. And this one's an even function. Absolute value of x from minus pi to pi. So it's just this looking thing. So the function it converges to is that v and its infinite number of clones. It's going to come out looking like all these triangles. So this, and there's no point of discontinuity here. So that's what our Fourier series will converge to without doing any calculation. And because it's even, we don't have to compute the b's. We just compute the a's using this middle column of formulas. Here we have this function, we have like a u cosine u du type thing. So I'm just using a table for how to do that integral. But I'm not going to go through this calculus. Hopefully you can do calculus. The only thing in there is, again, we have a cosine of n pi. So we can replace cosine of n pi with minus 1 to the n. That's the only trick beyond doing the integral. And that completes Fourier series. So we had the exponential Fourier series, the general trigonometric Fourier series, the specific cosine and sine series when you have an even or odd function. All right, on to new stuff next time.